So this is 3.6a in college algebra, and the name of this section is Polynomial and Rational Inequalities. So just as ax squared plus bx plus c equals 0, ax squared plus bx plus c can be greater than, less than, greater than or equal to, less than or equal to 0, and this is what we're going to look at today. So we start off with example 1. X squared minus 4x minus 5 is less than 0. So what are they asking us to do? They're asking us to find all the values of x that make this a true statement, that make this side of the inequality less than 0. So if I first make it equal to 0, I'll find out the biggest number that can be used here, and then I know everything else has to be smaller. Alright, so let's rewrite this as equals 0 there, and go ahead and solve it. Two binomials, and we get x plus 1, and we get x minus 5. So therefore our zeros are negative 1 and 5. The x-intercepts of the graph are negative 1, 0, and 5, 0. That's where it crosses the x-axis. So there's my graph, and let's put those on here just so I know where it crosses the x-axis. And because it's a quadratic, x squared, I know it's going to be in this shape here. So at least I know what it's going to look like, and I get that from the back of your book, the Library of Functions, because when you're dealing with an x squared, you're going to get a parabola like that. But I'm not going to go into all of the graphing on this, because that's not what the question is asking. It's asking us to solve it, but I'm just going to show you what this parabola looks like there. Okay, and then we're going to go ahead and continue to solve this. So we're going to divide this parabola up into everything to the left of negative 1, between negative 1 and 5, and everything beyond 5. So we've broken it up into 3 intervals here. So let's find out what's going on here. And rather than use this whole graph here, I am going to get rid of the graph, and I'm going to use a number line, because that's really all we need for this is just a number line, so we have our intervals. So there's our number line. We are at negative 1, and we are at 5. Alright, so our intervals are negative infinity to negative 1, and then negative 1 to 5, and then 5 to infinity. So for these inequalities, what we're looking for is, when is this value, when we put a number in here for x, when it spits out an answer, is that answer going to be less than 0? So actually what we're looking for is, when is the solution to this less than 0, or when is y less than 0? Because isn't that what this stands for? We plug in a number here for x, and it spits out a y value. Well, the y value is based on what this answer is. So what we're going to do is, we have some test values that we put in here for x. So we'll just put an x there. So we're going to put in a number here, here, and here that fits within that interval. So something between negative infinity and negative 1. Let's put a negative 2 in there. Something between, well, let's go ahead and do this then. So my f of x, or my y value, when I put a negative 2 in there, again, I don't care what the value is, I just want to know if it's positive or negative. So when I put negative 2 in here, I get 4 minus negative 8, so 4 plus 8 is 12, minus 5 is 7. So I get a positive answer. That's all I care about. When I put in this interval here, let's say I put in a 0, it's going to kick out, when I put 0 in this original problem up here, it's going to kick out a negative answer. It's going to give me a negative 5. And in the third one, when I put in a 7 there, and I put it in here, it's going to kick out a positive answer. Okay? So what am I interested in? I'm interested in when this answer, my y value, is less than 0, when my y value is negative. In this interval, this is the only interval where my y value is negative or less than 0. So my answer is going to be that, or I can write it as x such that negative 1 is less than x, which is less than 5. I can write it that way also. So either way, depends on if they want it in set builder or interval notation on which of these two you do. And that's it for that first example. So for example 2, we're going to do the exact same thing. So we're going to solve it as if it's equal to 0. Factor out an x. And x is going to be either a 0 or, well actually this is the difference of, let me keep going here, I left this as the difference of two squares. Because I'm going to have three answers. So that kind of clued me in. So my x is going to be 0 for that one, negative 1, or 1. Those are my three options. So we're talking about negative, oops, I'm going to do it down below here, negative infinity to negative 1. That takes care of that one. Negative 1 to 0, and 0 to 1, and 1 to positive infinity. So I have four different intervals there. So all I'm going to do again is I'm going to have a test where I'm going to put in an x value. And so for the first one, let's say I put in a negative 2, something between negative 1 and negative infinity. So when I put in negative 2, my f of x value, or my y value, is negative 6. So that's a negative answer. Let's do this in red. And when I put in, I don't have much of an option there, 0, negative 1, I'm going to have to put in a fraction. So I'm going to put in negative 1/2. And when I do that, it spits out a positive 0.375, or let's see, 0.375. What is that? Is that 3/8, I think? And that's a positive number, but so I don't care what the fraction is. I just want the answer. And I'm going to put in a positive 1/2 there, and that gives me a negative answer. And then I put in a positive, I put in a 2 there, and it kicks out a 6, which is positive. Okay, so what am I interested in? I'm interested when this value is greater than 0, or when y is greater than 0. And that occurs here and here. Okay, and if you look at the graph on page 321, it tells you in the little blue shaded part of the graph, tells you when that graph is above the x-axis, when the y value is greater than 0. Alright, so then all you have to do is write your answer down as negative 1, 0, unions, let's see, 1, infinity, or if you want to write it in set builder notation, which I suggest you do it both ways just because it is just a good reminder if you ever take calculus or another upper level math course, which calculus is the next one to take, being able to do that in both ways, interval notation or set builder notation, is just always good to practice on. Alright, so there we go. That's example number 2. So not too terribly impossible yet. So here's example number 3, and right above example 3 is a box on how to solve polynomial inequalities, so it just kind of goes through the steps that we've already done here. Alright, so first step, we're going to set this equal to 0. So by the time you move everything over and get everything in the right order, you get this. And how do you solve that? Well, if you look back on page 293, section 3.4, example 5, there is this exact problem and how to solve it. You've already done this in 3.4. I'm not going to take the time to actually solve this because we did this in 2 sections ago, and you should be able to do this. So we end up getting, for our answer, -1, 2 minus the square root of 2, 2/3, and 2 plus the square root of 2. Okay, so there's a 4 there. We got 4 answers. So, what do our intervals look like? Our intervals look like this, and we'll do them in red here. -infinity to -1. -1 to 2 minus the square root of 2. 2 minus the square root of 2, 2/3. 2/3, 2 plus square root of 2. Running out of room. Let's see if I can move this. There we go. And lastly, 2 plus square root of 2 positive infinity. So I've got 5 different intervals then. Okay, so then we use our test values. So for our test value for this first interval, somewhere between -infinity and -1, we're going to use -2. And when we plug -2 into this original problem, it's going to kick out a 112, a positive. Okay, so we're going to put the sign right there. When we plug in, let's say, 0 here, it's going to kick out a -4, so it's going to give me a negative. And this one, they put in 0.6, and we get a 0.0128, but the thing we care about is that it's positive. Here we plug in a 1, and it kicks out a -2, so that's our negative. And here we're going to put in a 4, we get a 100, and we get a positive. Okay, so what does that tell us? It tells us in our original one, I went right away and went from this inequality to this equality. So when I pulled everything here, originally this was really less than or equal to 0, and then I set it equal to 0 in order to get my intervals. But I'm interested in when the y value is less than or equal to 0. So here and here are the 2 intervals I'm looking for. So, because of the less than or equal to sign, I include my numbers in here. So, so there's one of my answers, and that unions with 2/3, 2 plus square root of 2, that, and I'm done. Okay, and if you wanted to use set builder notation, you would end up with kind of a long drawn out x such that -1 is less than or equal to x less than or equal to 2 minus square root of 2, or 2/3 is less than or equal to x, which is less than or equal to 2 plus the square root of 2. So you get kind of a long one, but basically it's x between those and x between those. So anyway, that is example 3. Now we've just got, looks like, one more problem, and then we'll be done, so I'll do that on the next video, 3.6b.